So we want to define cohomology groups with compact supports. But before we do that, we have to first define these cochains which have compact support. And basically what compact support means is that these elements of the cochain, say phi, are 0 on chains which are not in a compact set, say k of x. So this will become clear in a minute. So let us first write down the cohomology groups. So these cohomology groups will be defined sooner as algebraic limits. But these cohomology groups come from cochain complexes, and these cochain complexes with compact support essentially are nothing but a union of certain subgroups. So when you say cochain with compact support, it is nothing but a union of cochains of the form like this, x comma x minus k. What it essentially represents is nothing but, say, an element phi of the cochain. It vanishes on x minus k, that is, it vanishes outside set k, which is a compact set. So you have to take this set, a compact set, and vary over all subsets of x. So then you will get a cochain with a compact support, because basically other than the set k, it will vanish outside set k, that is, it will vanish on x minus k. So you take union of all such cochains which vanish outside these compact sets. Now notice the following inclusion, so k is a smaller space which is included in a bigger space, and then you have the corresponding map in the cohomology groups. Notice the direction of arrows. This is precisely because k and l now have complements there. We generally know that the arrow goes in opposite direction. Here arrow is going in the same direction because of the complement of k and l on either side of the equation. So we want to describe these cohomology groups with compact support, and obviously we will have to describe them precisely in the way we could describe the cochain complexes with compact support. So we said the cochain complexes we have described above. So we want to describe these cohomology groups with compact support as something like this. So basically it should consist of those elements of cochain which are not co-boundaries, and essentially all these elements come from the cochain complex. So as you vary k, they vanish outside k. So their support is just the compact set k, and outside k they just become 0. So in order to do so, we need algebraic limits. So these algebraic limits are nothing but direct limits. So let us now start the description of these direct limits. So start with abelian groups. We start with the abelian group G alpha. This is indexed, say, by a partially ordered index set I. Now this index set has an important property. So the important property is that if you have two elements, we will call it two elements as a pair, alpha beta element of I, then there exists an element gamma in I such that alpha is less than gamma and beta is less than gamma. Less than equal to gamma, alpha is less than equal to gamma, and beta is less than equal to gamma. And such a set I is called directed set. Now for each pair like this, alpha less than equal to beta, one has a homomorphism. So for this pair alpha comma beta, we will say alpha is less than equal to beta. We have a corresponding homomorphism given as follows. F alpha beta. So this basically you are going from one group to another group. Now this is such that F alpha alpha is the identity for each alpha. So if we have something like this, alpha is less than equal to beta is less than equal to gamma, we get the following commutative diagram. So we could go from G alpha to G gamma via F alpha gamma or via F alpha beta and then F beta gamma. So F alpha gamma is a composition of F alpha beta and F beta gamma. So this data like this, which is just given now, is called a directed system of groups. So now we want to come to the heart of the matter, which is the direct limit. So the direct limit of such a directed system is given as follows. So you take a disjoint union of all the groups and modulo it out by an equivalence relation. So what is the equivalence relation? So you consider an element X alpha in say some group G alpha, another element X beta and G beta. These two elements are equivalent if they are somehow eventually equal. So these are equivalent if there exists some gamma which is element of the directed set I such that F acting on F, obviously alpha gamma acting on X alpha is equal to F beta gamma acting on X beta. Now you can clearly see this relationship is an equivalence relation because it satisfies all the three properties. Reflexivity and symmetry is easy to see, and transitivity just follows from the directed set property. So heuristically we can say that these two elements are equal if they eventually become equal in the directed system. So it is just like Cauchy sequences that eventually you become equal. So let us write down the observation. So heuristically, two elements in disjoint union are equivalent if they are equal via these maps f alpha or f beta acting on them for some, so yeah, for some gamma they become equal in G gamma. So heuristically, two elements in disjoint union are equivalent if and only if they eventually become equal in some other set. Yeah, so you apply maps to it and they become equal in some other set. So say in set G gamma. So they eventually become equal in some directed system. So now let us apply the definition which we have just given on previous slide to the cohomology groups. So again we start X and we take a collection of subspaces X alpha and these set subspaces X alpha now form a direct set with respect to the inclusion relationship. So what we want to do is we want to now define homology groups. So if you want to define homology groups, so notice I'm talking homology groups, not cohomology groups. So you fix an I and a group G and you form a directed system. So obviously this directed system comes from the inclusion maps. So the reason why we took homology groups is to make the argument easy. So we can talk about natural maps. So yeah, homology, the direction of the arrow is covariant. So we don't have to worry about the direction of the arrow. So we get these natural maps. Now we want these natural maps to induce a map in terms of direct limits. So the question obviously arises, how does this map arise? So obviously you have seen direct limit is nothing but a disjoint union modulo some relationship. So what is a disjoint union? So disjoint union occurs over all these directed sets. So you take X alpha 1, so this is included in the map above in the direct limit. Then X alpha 2, it is also included above in the direct limit, because direct limit is nothing but a sum. This is alpha 2 and again this goes to hi x comma g. So we have these direct limit is nothing but this direct sum and the sequence of homomorphisms we have. So yeah, so the direct limit consists of all these groups on the left as a direct sum, and the mapping is nothing but this series of maps say f alpha 1, f alpha 2, f alpha n. So again, all the maps on the left, they form part of the direct limit. So yeah, these groups on the left be part of the direct sum, and then f alpha 1, f alpha 2, f alpha 3, f alpha 4 all the way to f alpha n form the part of the homomorphism. So now we come to the important proposition 3.33. Say X is a union of directed set of subspaces X alpha, and we have a property that each compact set in X is contained in some X alpha. So the idea is we want to talk about this natural map, the direct limit of the homology groups to the space is an isomorphism. So I will repeat it again. X is a union. So if X is a space which is a union of directed set of subspaces X alpha with the property that each compact set is contained in some X alpha, then the natural map, which we just talked about on the previous slide, so this natural map is an isomorphism for all ing. So we have to prove two things. We have to prove surjectivity and we have to prove injectivity. Both of them are easy in this case. So you start with surjectivity. So you take space X, and the space X has a cycle, and this cycle in X is denoted by a finite sum of singular simplices. So this is standard, nothing new here. The idea is this, that the union of images of these singular simplices, so whatever singular simplices we have, we can take the union of their images, and this union is compact. So since it is compact, it lies in some X alpha. Thus the map is surjective. So the argument anyway boils down to compactness. So every cycle in X has to come from some X alpha precisely because of the compactness. So we are just writing this down. Similarly, this goes for injectivity. So thus this map is surjective. The direct limit to between homology groups is surjective. Now we want to talk about injectivity. Now the injectivity would be violated if a cycle in direct limit gets mapped to a boundary. But again, this would not happen because of compactness. So I will repeat again, injectivity will be violated if a cycle in direct limit gets mapped to a boundary. But this will not happen because if a cycle in some set x alpha is a boundary in x, so just in case cycle from some set gets mapped to a boundary in x, then compactness would imply that this cycle gets mapped to a boundary in some set x beta which is larger than x alpha. So you have injectivity. And that is precisely what I am going to write. Now all this you can find on page 244 of Hatcher. So yeah, I will repeat again. If a cycle in some x alpha is a boundary in x, the compactness would then imply it is a boundary in some other x beta which contains x alpha. Yeah, so thus it represents a 0 indirect limit, and that proves the injectivity. So now we can give another definition of cohomology with compact supports. Yeah, and this is given in terms of direct limits. So we have discussed direct limits till now, and we are now going to use these direct limits to give an alternate definition of cohomology. So with compact support essentially means that the underlying sets are going to be compact. So if you are given a space X, obviously it is consisting of like small compact sets. So space X is made up of compact sets, say K, L, and so on. Or say K1, K2, K3. And all these sets are contained within each other. So you have something like directed sets. So, and they are under inclusion. So you should think of this as an increasing sequence of sets. K1 is contained in K2, K2 is contained in K3, K3 is contained in K4, K4 is contained in K5, and so on. So you have this directed increasing sequence, and its entire union is X itself. So we have a directed set. So obviously once we have this directed set, now we want to associate groups with it. So the only group which we want to associate are the cohomology groups. So you have these directed sets, say K1 is contained in K2 is contained in K3 and so on. So this is, you can consider as the index, and then you have the associated groups with it. So to each component like this, you associate a group with it. So the group is precisely this one, the cohomology group Hi x comma x minus k. And the coefficient group is G. You could actually should write R here. I'm just being consistent with Hatch's notation, and R will like help you get rid of the example of direct limit which we have in mind. So we have the I fixed. I is fixed and the coefficient group G is fixed. Yeah, so you just fix I and you fix G and you take K as a subset of X. Now we want to form these directed sets. So K has to be contained in L, say a bigger set L. So K is contained in a bigger set L. So corresponding to this, we should have a homomorphism. That is the standard principle. You have a directed set, which is inclusion of sets, and then you have the corresponding homomorphism. Yeah, notice that the homomorphism is in cohomology groups, and the arrow is going from x comma x minus k to x comma x minus l. That's precisely because of the complementarity. We are talking about x minus k and x minus l. If we were talking about k and l, then the arrow would have been in the opposite direction. So we have these natural homomorphisms. Yeah, we have a direct set and we have these natural homomorphisms. So thus you can define a limit group. So from this directed system, you have a limit group. Now you should always think of this limit group as the direct sum of all these cohomology groups with certain conditions. Yeah, so direct limits, you should always think of this direct sum of groups with this condition that some of the elements which eventually become equal, you modulo them out. So this is isomorphic to this cohomology with compact support. So we want to prove the equality above between the left hand side and the right hand side. You know the left hand side is nothing but a direct sum in which some elements become eventually equal, and right hand side is nothing but a cohomology group associated with the compact space, and in any case I is fixed for both of them. So we want to have this correspondence. So what are the elements of the direct limit group? Obviously elements of the direct limit group come from the corresponding cochains, which will be in the cochain complex, or I should say cocycle. Yeah, each element of this direct limit group is represented by a cocycle, and this cocycle obviously lies in a cochain of the form Ci x comma x minus k comma g, precisely what I have written for Hi. Instead that I will write Ci. So when is such a cocycle 0? So such a cocycle is 0 precisely when it is 0 on the right hand side also. Why we say that is so? Because if it is 0, that means it is eventually it is getting modulo out. Yeah, so you know it is getting modulo out of the direct sum. So it will get modulo out of direct sum if and only if it is equivalent to some other cocycle in some other cochain. Now what is that cocycle is going to be? That cocycle is obviously going to be some other group L which is contains K. Yeah, so this cochain is eventually equal to this, and therefore it is 0. So yeah, so thus we say that there is a equality above. Yeah, so the cocycles come out if and only if they are co-boundary of some cochain. Yeah, so yeah, you apply delta to it. So they are eventually equal means eventually equal via a delta map. So when I am saying eventually equal means eventually equal via a delta map. So basically co-boundary of a cochain. Now the last step is to show that we want to remove the C out of this cohomology group, and how do we do so? Now this is easy. We just notice that these cochains with compact sets are equal precisely because X itself is compact. So you have this increasing sequence of sets which I said at the start of the slide. K1 is contained in K2, K2 is contained in K3, so on and so on. And all this end up at X, because X is itself the unique maximal compact set. And therefore there is this equality. So yeah, that is pretty much it. Construction is extremely important. You should remember this, because this will be used in the proof of Poincare duality, specifically lemma 3.36.